very, very briefly, an idea of what inference means in a simple network, okay, like the ones we saw now, and then we go for inference on larger structures and techniques for inference in larger structures. But it can be useful in order to understand what it means to, change, play with probabilities in order to get inference. So we had the case in which we have this network, okay, with just one table with two possible values for B, for F, and then this conditional probability table for G, G given B and F. And then we are interested in computing probability of F equal to 0 given G equal to 0. And this you can't compute directly because the only things that you have in your conditional probability tables are G given B and F and P of B, P of F, okay? Now what you need to do is you need to play with probability rules in order to transform this formula into something which combination of something, each of which pieces you can read on your tables, okay? This is what you need to do in order to do inference, okay? So first of all, here you have basically G given B and F, and not F given G, okay? So you need to invert the relationship between F and G. And here is where Bayes' theorem comes into play, and the reason why they're called Bayesian networks, because they use a lot the Bayes' theorem for these inversions, okay? So by the Bayes' theorem, you know that F given G is equal to G given F times F divided by G, okay? This is just application of the Bayes' theorem. Now you're not done yet because P of F equal to 0 you can read is 0.1, okay? But these two you cannot, okay? So you need to also bring this into, this should go into something like G given F and B, and this again into some combination of G given F and B and something else. And so here is the derivation, okay? G given F, okay? You need to, this is also useful in order to understand the reasoning behind the inference, okay? Here what you need to do is, in order to come out with something which you can read from the tables, you need to introduce B, which is not here, okay? And every step has to be correct in terms of probability rules. So the only way to introduce B is by inverting marginalization, okay? So G given F is equal to G and B given F summed over B, okay? This is like when I was saying P of X and Y, you sum over Y, you get P of X, okay? You can do vice versa. You can say that P of X is equal to P of X and Y summed over Y, okay? And that's what I'm doing here. I'm saying G given F is G and B given F summed over B. These are all Boolean variables, so the values are 0 or 1. So you sum over two possibilities. Now here you're not done yet because you have in your table G given B and F and not G and B given F. And here you can use the product rule to do G and B given F is equal to G given B and F times B given F. This is product, okay? You took B on the other side, okay, times B, okay? This is actually a slight generalization of the product rule because P of A and B given C is equal to P A given B and C times PB given C, okay? There is a given something that you have to retain in every step, okay? So this is like PA and B is PA given B times PB, and then you add given C everywhere, okay? And now here you are done because this one is in your table, okay? G given B and F, okay? For each possible value on B. For instance, if B is 0, G0 given B0 F0 is 1 minus this. G1 given B0 F0 is 0.1. G0 given B0 and 0 is 0.9, okay? And you can replace it. Whoop. here, okay, B given F is equal to B, okay? Okay? Because B and F are independent, okay? If nothing else is given. And so this is just P of B, which you can read, okay? And this allows you to compute this stuff by combining pieces of probabilities that you know, okay? And the same you can do for the denominator, G equal to 0. Again, here you only have G, you need B and F, so you have to sum G, B, and F over B and over F. And now this, G, B, and F, is the joint probability of G, B, and F, which is, according to your Bayesian network, decomposed as G given B and F times PB times PF, okay? Because of the structure of the Bayesian network, okay? And now, all these pieces you can compute looking at the tables, okay? This is basic inference, okay, with few variables, okay? You have to do all this kind of machinery, no, to come out with combinations for which you can read values on the tables, okay? Now, all this is like kind of, mechanics steps, so available software tools do that for you. Huh? Problem is that these can be quite expensive if you have large networks, all these kind of summation, marginalization out variables, and so on. And I will give you some hints on how to do this efficiently with exploiting the structure of the network. There is a lot of work on inference in Bayesian networks. I will give you an overview and some hints to more advanced stuff, okay? Now, first of all, the typical task of inference, and it's the same as we saw before, is you want to compute the probability of some variable of interest given the evidence that you collected so far. Okay, so in the previous case, the evidence was the gauge reads empty, the battery is flat, and so on. Okay, and you want to compute the probability of one or more variables of interest given the evidence. Okay, and so typically, let's say the most common inference task is actually there are two, but let's say the most common is computing the probability of some variable of interest given the evidence, okay? Now here, I need to distinguish between the random variable and the realization, okay? So I will use uppercase for the random variable and lowercase for the realization. So capital E equal to E means evidence variables in E take value vector E, okay? Sunny, yes, I don't know, rainy, no, and so on, okay? Okay, first of all, Bayesian networks represent joint probabilities, okay? And when you do inference on Bayesian networks, you end up computing joint probabilities, okay? Even if you put evidence, and I will show you how to do that, when you do the reasoning, you will end up having a joint probability. So you will end up producing the probability of X, the variable or variables of interest, and the evidence, okay? While you usually are interested in the conditional probability given the evidence, okay? And now you will use the product rule to compute X given E as the joint probability of the variables of interest and the evidence divided by the probability of the evidence, okay? The probability of evidence is very simple to compute because once you have this, you just sum up over X and you get the evidence, okay? So when you have the numerator, the denominator is simple, okay? Now, this is a joint probability, okay? It's your network, okay? Maybe X can be few variables or the entire set of variables, okay? And E is the evidence, okay? So you could take the joint probability, put the values of the variables that you know, the evidence, and compute the joint probability, okay? But the problem is that, suppose I'm interested in computing the probability of one variable, okay? You have evidence on two variables, and you have other 200 variables for which you don't have evidence, okay? And you did sum them up in order to compute the probability of that variable. You have to marginalize them out, okay? Probability of one variable, you need to sum over all the others to remove them from the joint probability, okay? And this explodes combinatorially, okay? If you have, let's say, binary variables, right? You will have two to the number of variables possible configurations for them taken all together. If you have k possible values for each variable, k to the n. So it grows exponentially with the number of variables, okay? So you can't really say, okay, let's sum everything up. You get an exponential explosion in summations, okay? And it gets intractable, okay? So you need more efficient ways to do this inference, okay? And I will show you how to do that, okay? This is really the very basic things that you need in order to even start thinking about inference on anything more than few nodes, okay? And now let's start with, and let's say detail this for chains, because it's quite a useful type of networks and it's reasonably easy and intuitive to see what happens here, okay? Now, a chain is a sequence of nodes connected by arrows. It can be a chain of causation. It can be a temporal chain. We talked in the break. You can think about Markov chains, hidden Markov models, these kind of probabilistic models which evolve over time, for instance. And now let's see what happens here, okay? The probability, okay, of the network, of the variables in the network, the joint probability, so capital X is the vector of all the variables, decomposes as, again, node given parent, P of x1, P of x2 given x1, x3 given x2, and so on, until xn given xn minus 1, okay? Every time node given previous node, okay? And now, suppose you're interested in the probability of a certain variable, x lowercase n, anywhere, at the beginning, at the end, whatever, okay? It's the variable you're interested in, okay? Now, marginalization tells me that the probability of one variable is obtained from the joint probability represented by the network, summing up over the values of all the other variables, okay? x1, x2, up to xn minus 1, then you skip xn because it's what you are interested in, and you go xn minus 1 up to x capital N. You sum over all other variables, okay? You have, say, binary variables. You have n capital N minus 1 of these. How many summations you have to do? You have to consider 2 to the n minus 1 possible configurations, right? And you die. But now, if I take this summation and I apply it to the decomposition of the network given by the chain, okay, now you see that the sum over xn, capital N, only involves, let's say, affects the last piece of the decomposition, okay? Because x capital N doesn't appear anywhere else, okay? So you can take this summation and bring it up along the sequence to the end, because all the rest is constant, okay? And do the final summation, okay? To do the final summation, okay, this is Pxn given xn minus 1. If you sum over xn, first of all, this is a probability of which depends on two variables. If you sum over one variable, you still get a function, okay, of the other variable, okay? If the variables are binary, you get two values. The value for xn minus 1 false, the value for xn minus 1 true, okay? So for binary variables, this is actually a two-value table, okay? For continuous variable, it's a function. Now, if you think of it, anybody tells me, by eye, what is this value? Sum over xn of p of xn given xn minus 1. Let's think of the example. It's raining, given that, let's say, it's sunny. Okay. Given that it's sunny, okay, xn is raining. So if you sum over it's raining and it's not raining, what do you get? 1. Okay? Because given something, the remaining variable, if you sum over its values, you get 1. Okay? So in this case, this value is actually 1. Okay? Now I keep this representation because when we put evidence, that's not going to be 1 anymore. Okay? But in this specific case, when you have no evidence, this is just 1. Okay? So you backpropagate 1. Okay, now I can apply this kind of reasoning multiple times. Okay, now I took sum over xn of pxn given xn minus 1, and I replaced it with mu xn minus 1, a function of xn minus 1. Okay, and I remove this from the joint probability, replacing it with this value. Okay, and now I'm left with all the other summations. Okay, and a function which depends on all the variables up to xn minus 1, but not on x capital N. Okay, and then I can repeat this operation, okay, over xn minus 1. What are the pieces of the joint probability which depend on xn minus 1? What I just computed, okay, plus pxn minus 1 given xn minus 2. I'm going back in the chain. Okay? Now I multiply these two things. I sum over xn minus 1. There is nothing before which also depends on xn minus 1. So I can forget about what's before. Okay? So I sum over this, and I get again a message which depends on xn minus 2. Okay? I call B these messages because they are backward, because you are going backward along the chain. Okay? So if any of you is familiar with dynamic programming, this is dynamic programming. Okay? So I go down, aggregating these values until I reach the variable I'm interested in. Okay? Now the message, okay, the value, which depends on x lowercase n, is computed by taking mu beta of n plus 1 times p of xn plus 1 given xn, summing over xn plus 1. Same as this, okay, for the node I'm interested in. Okay? And now, this basically, if you want, it's all the summations up to from the end down to xn. Now you still have sum over x1, x2, and so on. So you do the same reasoning from the beginning up to xn. Okay? Now the first message, okay, is you sum over x1. And here, watch out, because the network is not symmetric. You have px1, px2 given x1. Okay? Because x1 has no parents. Okay? So the piece of the network which depends on x1 is p of x1 times p over x2 given x1. Okay? There are two pieces. If you sum over x1, okay, this is a function of x2. Okay? And this is what you replace this summation with. Okay? We call this mu alpha because the other is beta, and so you call it the other alpha. You could call it forward. Okay? This is, by convention, usually you call it alpha. And then you will do the same. So mu alpha of x3 is the sum over x2 of mu alpha of x2 times p of x3 given x2. Okay? And so on. aggregating until you get to mu alpha of xn. At this point, you ate all the summations, okay? And p of xn is just the product of these two values, okay? And if you think of it, each computation involved one summation, okay? So k terms, if you have k possible values. And then you have n minus 1 of these. So you have n minus 1 times k instead to k to the power of n minus 1. So you went down, no? From the exponential case, which is what dynamic programming does, okay? Now, you can think of this as a message passing process, okay, in which this mu alpha and this mu beta are messages going forward or backward along the chain. So mu alpha is a message which goes from the previous node to the node which is here. Okay? So mu alpha of xn is a message which goes from the previous node to the variable xn. Mu beta of xn is a message which goes from the following node back to xn. And when you are here, you just take the product of the messages. Okay? So message passing algorithm is really a matter of locally computing messages, sending them in the network, and aggregating them where you need to do the eventual computation. Okay? And using, in this way, dynamic programming procedures in order to break down the computation into pieces to be propagated. Okay? This is the very basic step for making inference efficient. Okay? Now, there is one a caveat, if you want, that if now I'm interested in computing px n plus 3, I have to restart the process again. Okay? Start from the end, you get down to n plus 3, you start from the beginning, I go up to n plus 3, and I do the product. But most of these messages were already computed for computing p of xn. Okay? All the ones up to xn were already computed. All the one down to xn plus 3 were already computed. Okay? Right? Well, I have it here. If you look at this network, right? If I want to compute p of xn plus 1, I already computed all these messages. Actually, the only message which I miss is message from xn to xn plus 1. But all the others are already computed. Okay? So in general, instead of recomputing everything from scratch, what you do is you take a message from the beginning, you send to the end. Then you take a message from the end, you send to the beginning. Okay? And now you have all messages in all directions, and you can compute any local probability you're interested in. Okay? This is called full message passing. Send message from the beginning to the end, message from the end to the beginning, and you do whatever you're interested in. Okay? Now, what about evidence? Okay? This procedure tells you what is the probability of one node, okay, by summing over all the others. What about evidence? We said that in inference, usually I'm interested in computing the probability of something given the evidence. Okay? And now evidence is pretty simple because we saw that for all the variables which are not the target one, we were summing over their possible values. But if you have evidence, it means that you know its value. So instead of summing over the values, you just plug the value. Okay? And you go on. So that message, instead of summing over the possible values, will use the value that you know. Okay? So, for instance, simple case with a chain with 4 nodes. Okay? Suppose you're interested in computing the probability of x2, okay, given x1 that takes a certain value, xe1, and x3 that takes a certain value, xe3. Okay? Now, you do this message propagation step, okay? But what you do is when you go for x1, instead of summing over x1, you plug the value, okay, of the evidence, okay? When you go for x4, you sum over x4, okay? When you go for x3, you plug the value, okay? So anytime you have evidence, instead of summing, you plug the value, okay? This, okay, is the joint probability of the variable of interest, the evidence, okay, the variable which are neither what you are interested in nor the evidence get summed up, okay? So this is the joint probability of node of interest, evidence, and x summed over, and x4 summed over x4, okay? So it's basically this, and this can, as you see, I'm bringing the summation to the end, okay? In all other pieces, I don't have summations because I just plug the value, okay? So when you send messages, you send a message which is either a summation if the variable is not observed, or a computation in which you plug the value if the variable is observed. But the procedure is exactly the same. The only problem is that this produces a joint probability, not a conditional probability, so you have to do the normalization, okay, which consists of taking this joint probability and dividing by the probability of the evidence, which is obtained just taking this and summing over the variable of interest. So in the previous case, you take this stuff, you sum over x2, and you get the probability of this, which is the evidence, okay? Marginalization, you take this stuff, you sum over x2, you get this, which is the probability of the evidence, okay? Now, you divide this by the evidence, and you get the conditional probability, okay? Now, there is actually one other type of inference task that we are typically interested in, which is called most probable explanation, map inference, depending on what variables are you interested in predicting. But let's focus on most probable explanation / configuration, okay? Which is, in a sense, the most common. And this is the task, okay? You have, let's say, certain joint probability distribution, and you want to say what is the most probable configuration for all the variables in the network, okay? If I need to decide, okay, what is the configuration of the variables, I have to take one configuration. I would like to have the most probable, okay? And then if I have evidence, I want to find what is the most probable configuration of the variable for which I don't have evidence, given the evidence, okay? Now, finding the most probable configuration, what it means, you have the probability, you want to do the max over the variables, and takes what variable maximizes the probability. So do the argmax, okay? And this is the configuration which has maximal probability. Now, what is the problem with this? I could say, okay, for each variable, I do the previous approach to get its probability, P of xi, okay? And then I say, okay, P of xi, you maximize over the values, and you get the value for xi. You do the same for xj, you maximize, and you get the value for xj. And you do it like this for all variables, okay, independently. But this is not a jointly optimal configuration, okay? If some variables are in conflict, okay, think of the earthquake and burglar, okay? Could be that you have the alarm, okay? Both events have more than 0.5 probability maybe, because some reason there should be, okay? But it's quite unlikely that the most probable configuration is that you have an earthquake and a burglar jointly, okay, simultaneously, right? So if you maximize separately, you would end up having a configuration which is locally maximal for each variable, but not necessarily globally maximal, okay? Now, what you need to do is something different, which is still pretty similar to the previous case, which is you want to maximize over all the variables, okay, the joint probability, okay? Now, maximizing over all the variables means maximizing over x1, x2, up to xn. Again, here I'm talking about the chain. And now, again, much as before, okay, the maximization over xn only affects the part of the decomposition in which xn appears, because the rest is constant. So you can bring the maximization down to the end and maximize over xn, pxn given xn minus 1. Okay? The rest is constant. Okay? And now you do this. Okay? This is a function of xn minus 1. Again, you replace this max with that function, and you go on to xn minus 1. Okay? The only thing that changed with respect to the previous algorithm is that you replaced sum with max. Okay? But the algorithm is exactly the same. The previous one was called sum product. This is called max product. Okay? If you read this algorithm as max sum, it's because of underflow issues. If you take a product of probabilities, they go down to 0, so you work with logs in order to avoid underflows. So I don't want to go in these technical details, but if you read max sum, it's the same thing, only, let's say, caring for underflow issues. Now, there is one caveat with this, okay, which you see here, okay. Now, let's say we start from the beginning, okay. You send this max message up to the end, okay. You get to the end of the sequence, okay. Mu alpha xn, okay, the message that you collected. If you maximize over xn, you get the overall maximal probability, okay, because you collected max messages. And also, you know what is the best value for xn, okay? The xn maximizing that final piece, okay? So max over xn of this last message gives you the maximal probability, okay? Arg max over xn of this last message gives you the best configuration for the final variable, okay? But what about the other variables, okay? You want to have the configuration for all the variables in the network, okay? In order to have an entire maximal configuration. You know the probability now, you know the configuration for the last variable, what about the others, okay? In order to recover, these messages that you send depend on the following variable, okay? So you don't know the best configuration until you reach the end, okay? Because maybe at some point something is very promising, then there is a step in which it has a very, very low probability. So some other less promising configurations raise their probability of being the best one, okay? So in order to recover the maximal configuration, you have to keep track of another type of information, which is what were the configurations maximizing the message that you sent, okay? So let's look at each local message, okay? Local message is the message, okay, from xi minus 1 to xi along the chain is what? The message from xi minus 1, the previous message, times the local probability, xy given xy minus 1, okay, maximized over the previous variable, Okay? This is the message sent to the next variable. Okay? When you maximize over xi minus 1, okay, you compute the value, but there is also an assignment of the variable which produced that value, what is called the argmax. Okay? Now, again, these are functions of the destination. Okay? Say these are all binary variables. Okay? If my variable is, let's say, getting wet, let's say raining, I could, and the previous variable is cloudy, okay? I could say, okay, if the destination rainy is true, the most probable configuration is that it was indeed cloudy, and the probability is 0.3, okay? If the destination is rainy false, the most probable configuration for the previous variable is that it was not cloudy, okay? And the probability is whatever, 0.2, okay? So you have to send two types of messages. One message that says rainy true, 0.3, rainy false, 0.2. And another message which is rainy true, cloudy true, rainy true, cloudy false, okay? So the configuration for the previous variable producing the maximum, okay? So this other message that we call phi A, okay, is a configuration message, okay? Again, the best configuration for cloudy depends on what eventually is the best configuration for rain, okay? When you reach the end, okay, I say, okay, eventually I got wet, okay? So the final, most probable configuration for the final variable is true. Then I take the configuration message, okay? I plug the value for the last variable, and I recover the maximal value for the previous variable, okay? Like if wet is true, probably the most configuration for the previous variable was rainy, yes, okay? If I have this, I can backtrack again to the previous configuration message and get the best configuration for the previous variable, which will probably be rain, yes. The previous configuration is cloudy, yes. And you go back until you reach the beginning of the sequence, okay? So there is this kind of backtracking procedure which recovers the best configuration by reading the best configurations of the previous steps, given that the following step has been decided, okay? So this is how it works in terms of sequence of steps. The last best configuration is just obtained maximizing the last message, okay? And now once I have the last best configuration, I take the configuration message, plug the last best configuration, and I take the one but last best configuration, and I propagate until I reach the end, okay? It's simple to see this process by a kind of what's called a trellis structure, okay? Let's say that this is the sequence, okay, from 1 up to capital N. These colors represent different possible values for the variables. Suppose here that the variables have 3 possible values, rather than having always 2, let's say 3, okay? So, for instance, this one means that variable n minus 2 takes value 2, okay? Now, this configuration message basically links this trellis, meaning that here, okay, it tells that if the best configuration for the variable n minus 1 is red, then the best configuration for the previous variable is green. If it is blue, then the previous best is blue again, and so on. So you have this kind of, and then you go on, okay? And you have these kind of paths, right? When you reach the end, suppose this is the end, okay? The best here is red, is green for n plus 2. Then you read from the configuration message, which tells you that the best configuration for n is green again, and then you read back, okay? All the best configurations, okay? with this kind of backtracking step. Now, I talked about chains because they are a useful type of structure, and they are the simplest complex structure over which you can show efficient inference. Okay, this very same, or let's say very similar process of message passing can be done efficiently and exactly on other types of structures. Okay, which after some processing end up being trees. Okay, so you can do efficient inference by this message propagation on undirected trees, and I will be back a bit in a moment. Directed trees, okay, so trees where basically there is just one root with no parents, and then, okay, all nodes have a single parent. This is a tree. Polytrees, in which you can have multiple roots and nodes with multiple parents, but there is only one directed path between each pair of nodes. Okay? So if I plug another arrow here, this is not a polytree. Undirected trees, because I didn't talk about this, but these kind of inference processes work both for Bayesian networks and for another type of graphical models, which is called Markov networks. I don't know if any of you heard about them. It's undirected models. There are no directions in the arrows. It's another type of models which have some little bit other characteristics. I will not go into that because we don't have enough time. But it's when you go for inference, after some kind of processing, they end up using exactly the same algorithms. Okay? That's why it's useful to say this, because a Markov network, which is this structure, can have efficient inference by these message passing algorithms. Now, the trick for doing efficient inference on these structures is to take the Bayesian network, provided it satisfies that previous conditions, and turn it into an alternative representation, which is called factor graph. Okay? A factor graph is basically a graphical representation which highlights the decomposition of the joint probability into factors, okay? Local components. It has basically one node for each node in the original graph, and one node for each factor. And factor nodes are connected to variable nodes. It's easier to show examples. So this is, let's say, a sinc probability network. These are two possible factor graphs. Okay, let's look at this, which is the most, in a sense, complete. Okay, you have three factors, and in the factor, you basically put pieces of the probability in a way such that the probability of the factors recovers the entire probability. And each factor should be connected to all the variables involved in its local function. Okay? So for instance, here I have fc, which takes p of x3 given x2 and x1, and so it's connected to all the variables, the three variables. Then I have fa, which takes p of x1, and it's connected only to x1. And I have fb, which takes only x2, and is connected to x2 and is p of x2. So if you take the product of these three, you get the joint probability of the network. Okay? Now, the nice thing of this structure is that a generalization of the message passing on chains in these structures produce efficient inference. Okay? Now, I'm not giving you the details of this algorithm, let's say the formalization, because I don't think we have time for that, and probably it's not the best thing to spend time on. I will, if somebody is interested, I can show that later. But I think I can probably show it easier by an example. Okay. Here is a Bayesian network. Okay. PB given AC, PA, PC given D, PD. Okay, that's the decomposition. Let's build the factor graph like this. Okay. So I just name the factors with the pieces of the probability attached to them. Okay? So this is PB given AB, AC. This is PA, PC given D, PD. Okay? And now let's say we are interested in computing the probability of B. Okay? So in principle, I should take this and sum over all other variables, C, D, A. Okay? Now, I will do this by sending messages. Okay? And the idea is to send messages, all messages all the way to B. Okay? If I see this starting from B, it's a tree. Okay? With B as a root. Okay? So I can take the leaves and send messages from the leaves to B. And when the messages reach B, you take the product of the messages. And this gives you the probability. As in the chain, you were sending messages back and forth and take the product. Okay? Now here, these are the messages. Again, I will not give you the detail on the formalization, but show you a practical example so that you have an idea of how it works. The leaf factors send the factor themselves as messages. So this sends PA, this sends PD. Okay? The node messages, the variable nodes take the product of the incoming messages and send this message farther down. Okay? So A receives one message and basically propagates it because it has only one incoming link if the other is the destination link. Okay? So this just propagates PA, this just propagates PD. Okay? Now the internal factors, okay, take the incoming messages, multiply them by the probability they hold, and sum up over the variables which are not the destination. Okay? In the chain, you summed up over the previous variable. This, if you look at it, it's also a chain, so you sum over D. Okay? When you have more incoming links, you sum over more variables. Okay? But the idea is that here you take PD, you take the message coming from D, which is actually PD, you multiply by PC given D, and you sum over D. And this is a message sent to C. Okay? The same thing you do here. This is a variable node, so it has one incoming link, one outgoing link, so it just propagates the message. So the same message gets propagated. And now, this factor got a message from C, a message from A, and now what it does is take the product of these two messages, so message from A, message from C, okay, multiplies them by its local probability, B given AC, and then it sums over all the source nodes, so A and C. This contains A, C, and B. If you sum over A, C, it's a function of B. Okay? And then you send this message down to B. B has only one incoming link, so that message is the marginal probability. Okay? And if you think of it, the message from A here was PA. Okay? The message from C, we see it here, was sum over D of PC given D times PD. Okay? So if I plug it here, I get PA and sum over D of PC given D times PD. Okay? This is the local probability. I sum over A and C. And now, if I take the D out, okay, I get sum over A, sum over C, sum over D, PB given AC times PA times PC given D times PD. B given AC, A, C given D, D. This is the joint probability of the network. Okay? So you sum over A, C, and D the joint probability of the network. Okay? Which means A goes away, C goes away, D goes away, you get PB. okay? But you didn't do it like this, okay? You did it like this. So you did local summations. This is a very simple example, of course, but if you think on a larger network, this is what happens, okay? You do local computations and you propagate, okay? And this is how information flows, okay? So this is called, again, sum product algorithm for inference, and it allows to do efficient inference provided you can end up with these kind of trees when you go for factor graphs, okay? So it works for a number of networks, okay? There are some networks for which this procedure can't be applied because they don't produce trees when you produce the factor graphs, okay? And if you have cycles, this procedure doesn't work because the message goes in cycles, so it never reaches the end, okay? So inference in general networks is pretty complex, okay? When you talk about Bayesian networks, whatever on arbitrary networks is always NP complete, NP hard, and so on, okay? So when whatever means inference, it means many different types of operation that you could be interested in doing. So for arbitrary networks, everything becomes complex, okay? Which means, for instance, in the way to do exact inference on an arbitrary network, okay, which if you do the factor graph doesn't become a tree, is to produce a different structure, which is not a factor graph, but it's called a junction tree. I will not provide the details, but the intuition is that basically you collapse together variables, okay? So that nodes in this junction tree are not anymore variables, but they are collections of variables, okay? And then you connect them together. And in this way, you can end up producing a tree, okay, in which these message passing algorithms produce exact inference, okay? So they can be applied on these junction trees. But the problem is that each node has not one variable, it has a cluster of variables, okay? So locally there, you have to consider all configurations for those variables, okay? So if you end up having a big cluster, you are still in trouble because the complexity grows with the size of the largest cluster in the junction tree, okay? And for arbitrary networks, this is still exponential, okay? So in general, you can do that, but for arbitrary networks, it's not going to work, okay? It works for networks which are not factor trees, but they're not too much complex, okay? But for arbitrary networks, there is no way to do efficient exact inference, okay? Now, this is the reason why people also investigated a lot approximate inference, okay? Now, I will not go into details of approximate inference techniques, okay? I will give you some hints and intuitions on how they work, okay? There are three main techniques. The first two, in a sense, are similar, are from the same kind of class, but they are diverse enough to be distinguished. Loopy belief propagation is, in a sense, very simple. You take the original network and you send messages with message passing. You will have cycles, meaning not directed cycles, because in a Bayesian network you can't have a directed cycle, but you will have cycles in terms of paths, okay? So the messages will go infinitely, okay? But then what you do is you decide a stopping procedure, and they won't be exact. All these are approximate. There are variational methods in which you say, okay, inference on the network is intractable. I build a simpler network, okay, which breaks down some connections and so on. It simplifies the network. This simplified network, or let's say distribution, is parametric. And then I try to tune the parameters, maximizing the similarity between the two distributions. And then I do inference in this. This is why it's called variational, because you vary the parameters of your simplified version to match the original version. And then you do inference in that simplified distribution. Okay? And there you can do an exact inference. It's not exact because this is just an approximation of the original distribution. Okay? And then finally, the most common, in a sense, methods are sampling methods, which are doing probability computation by sampling over the network. And I will tell you a couple of words on the two, let's say, simplest, in a sense, to understand, which is message passing, looping message passing, and sampling, just 2 words. In the looping belief propagation, that's really very simple, okay? In a network, you can send a message after you received all messages but the destination. That's the rule, okay? In a chain, you take a message, you propagate. Here, this message could be sent if you received these 2. Okay. Now, this is a problem in a cyclic network. Okay. And so what you do is you basically assume that all nodes are in the condition of sending messages because you assume that they received one message from their sources. So everybody sends a message. Okay. And you can use a schedule for passing messages like flooding, in which everybody simultaneously sends messages. Okay? Now, at this point, at the next iteration, everybody will have received messages and can recompute the message to send using the messages at the previous iteration. Okay? And this can, in principle, go indefinitely. Okay? Now, if you're lucky, the next message will be the same as the previous message for a node. Okay? It means that nothing changes. If you're very lucky, all nodes will not change their messages, which means that you converged. Okay? If you're not very lucky, you will stop at some point, either because the difference in messages gets small or because you finished your time. Okay? The sampling methods, okay, are also reasonably easy to understand because the idea is this. Suppose you're interested, okay, in knowing what is the probability of some variables in the network, y, okay, possibly given the evidence, okay? Now, sampling works like this. You have a probability distribution, you sample from this distribution, you get configurations, and you look at how many configurations are consistent with what you're interested, with the values of y you want to compute. And the fraction gives you the probability, okay? So if, let's say, I want to compute the probability that it's raining, okay, I have a network with a number of nodes. I sample from this network. I get 10,000 samples. 2,000 are samples in which it is raining. So the probability of raining is 2,000 over 10,000, okay? Now, the problem is with this simple process is that typically it's not easy to sample from distribution. If it was easy to sample from distribution, it would probably also be easy to do exact inference. Okay? So what you need to do is a number of approaches, but Markov chain Monte Carlo, which is kind of most common, you basically build a process which samples from something which is progressively closer to the distribution you would like to sample from. So you have this kind of, and so basically, in a nutshell, you build a state. The state of the network is a configuration for the variables in the network. You move from state to state by changing values according to the probability of having these different values. And at some point in this process, the probability of getting a certain value will be the same as the probability in the original network, okay? I think I'll just say this because if I need to be more clearer, I need to be a little bit more detailed on what Markov chain Monte Carlo means, but I think you get the intuition, okay? So you have a process of generating changes in the configuration of the network that at some point samples stuff which has actually the probability of the original network. And then you can start collecting samples and doing statistics, okay? I think I'll stop here for now, because then I want to tell you something about learning. And as in the previous case, I have some appendices at the end with additional stuff, including a little bit more detailed sampling. Okay?